Welcome back to the Couch of Science. Today we are joined by Doug Mandu in a discussion on music theory. And we're going to have Chris help us out a little bit with this. How are you, Doug Mandu?
I'm doing good. How are you, Matt? Good to see you after all these years.
It's great to team up with you again. So for this, do you prefer Doug Mandu or Aaron?
Yeah, why don't we let's go with Aaron Katz. Why don't we? K-A-T-Z, Aaron Katz.
All right, so we are joined today with teacher, Professor Eric Katz.
Indeed.
There we go. And I am Professor DynaMatt McGillacutty.
Yes, you are.
We have Dr. O'Grady on guitar. So, so for people who have heard the term music theory but don't know anything about it, how would you describe it?
Well, it's an extremely broad term that could explain anything but the language of music itself, which is, of course, different for every kind of music around the world. They say music is a universal language, but they're wrong. It's not a universal language. The different musics of the world are different languages, just as are the different languages that we speak, and they have their own rules and their own music theory. So. But that would be just the sort of grammatical side of music theory. There's another side of music theory which deals with more scientific matters, like why do strings sound the way they do, and why do we tune instruments the way we do. This interacts with the language, but it can also be included within music theory. So.
Okay, so it's a broad term that has many definitions.
Correct.
We'll go with the American music term.
Sure. Well, what I'm actually going to talk about today is why music is broken and can never be fixed.
Okay.
And this is because of the problems of tuning the scales that we use. And the tuning of scales has evolved over many hundreds of years in order to account for different situations. And a lot of the things that we were trying to get in terms of the sound of these scales, it's when you put it together with other things we're trying to do, you just end up with a series of compromises that just ruin everything. And that's where we are today. The music we listen to today, it's completely ruined. So let me get to the details of why this is.
Why music is ruined.
Why music is ruined. So the first feature we have in music, and I can do this part, although I can use some help as well, is when you take a string. No, this is better on the string. Let's do this on the string. By the way, if I talk too fast, slow me down. I get excited. So,
No. Go ahead.
So, so let's look at a string. Why don't you play me the note A, for instance, on the A string. Now that note A, that's vibrating 111 times a second. When you vibrate the air up to a certain speed, you start hearing pitches, and that's what you're hearing. You're hearing the pitch A. Now, why don't you play us one octave above that at the 12th fret? So that note is A vibrating at 220 times a second. And in fact, if he could play those two A's together, or even octave A's together, why don't we play me an octave A somewhere? Now try to pluck them at the same time. Now you'll notice when you play the octave together at the same time, it almost sounds like one note. You can barely even tell that it's two notes, and that's because the 111 times a second and the 220 times a second synchronize. They're in phase so nicely that you can barely perceive that it's even two different notes, right? This is what we call a pure interval. The ratio of the octave to the fundamental is 2/1. And this is possibly the most fundamental interval there is. Little kids sing at higher octaves. Women typically sing at higher octaves than men. It all sounds like the same note. Everyone can sing it together, and it's as if they're singing the same note. No one has any problem with this. So the modern tuning system that we use on something like an accordion or a guitar, what they do is they divide that octave into 12 equal half steps. And the distance, the ratio between any two half steps is exactly the same. So for instance, if I play this chromatic scale, the distance between each of those half steps is exactly the 12th root of 2/1. That's the number that if you multiply it by itself 12 times, it will equal 2. And the reason it's such a weird ratio is it has to get you right to the number 2, right? So if you take 111 and multiply that, 110 for the low A here, and you multiply that by 1.059, whatever the 12th root of 2 is, it will, after 12 iterations, get you right to 2.0, the octave. Now, this tuning system is relatively recent historically, because in the past, music wasn't trying to do anything as weird as finding the 12th root of 2. It wasn't even possible mathematically before the late 1500s. People didn't even know how to calculate this. So what they were really looking for was pure intervals. Now, we've already talked about the first pure interval. That's 2 to 1. We still have that one. It's still 2 to 1. It's perfect. Then you get into the other pure intervals. The first one is 3 to 2. And that's the interval of a pure fifth. What do you play as a pure fifth? And you hear that sounds pretty nice, right? It just goes together. The next interval is going to be the 4 over 3, and that's going to give us a pure fourth when you play as a fourth. This is perfect for guitar because guitars are tuned in fourths, right? And then we get into the thirds. The major third is, at least theoretically, it's 5 over 4. Now, I don't know if you can hear this, but you'll notice that with the distortion on, that interval doesn't sound as pure, right? And it's because it isn't. So, maybe let's just try it. Let's see if you can go from the G string to the B string. Tune the B string slightly flat. We'll try to get it to be a pure third. It's somewhere there where it stops beating, right? So the quality you get from the pure intervals is there's no beats, right? So if you find your pure interval, and you've heard this when you've listened to guitars tune, they'll find that pure interval, and as they're slightly out of tune, you start hearing wah, you hear that beating. So what they're trying to do when they tune their instruments is to get rid of the beating, right? Now, the problem is that third is nowhere on the 12-note square root of 2 system. It's completely out of tune. Now, let's go into how these tunings evolved historically. And let me look at my notes here. So, the real problem comes when you have keyboards. Because keyboards, you can't change the notes. If you're playing a non-fretted instrument, or if you're singing, you can adjust your notes to get the intervals to be pure. So, one of the oldest systems that use pure intervals is a system called Pythagorean tuning, and it was devised about 500 BC. And what Pythagoras, or what his followers actually would do, is they would tune around to perfect fifths, perfect 3 to 2 ratios, nice pure tone. And they only needed to get to 7 notes. They weren't worried about all 12 notes back then. And that was a reasonably nice system to give you a bunch of pure intervals. The thing is, the music back then didn't use harmonies the way we do. They didn't sing more than one note at once, maybe a little bit in fifths, but it wasn't like today where we have all kinds of chords and harmonies, mostly melodic music, right? Now, the first problem they ran into with Pythagorean tuning is that if you tune your fifths around, we'll start at C, and go to G, and go to D, and go to A, and then you end up at E. You end up at E, that note is not a pure third from G. And what happened in Western music after about 1450 or so is they started to really play with those thirds. So they weren't as interested anymore in having the fifths be pure. Now they wanted the thirds to be pure. But it turns out this is a conflict. If you tune your keyboard so that your thirds are pure, then the fifths are out of tune. But they kind of went with that. And what they ended up with by the late 1500s is a system called mean tone tuning. So what they would do is they would get all the thirds pure, and they would tune all the fifths slightly flat, and they would just kind of give that up, but close enough, right? And meanwhile, the music was focusing more on the sound of those pure thirds. Now the problem is that if you tune your keyboard so that your thirds in C major are pure, you can probably tune it so keys that are close to C also have pure thirds. So G might have pure thirds, F might have pure thirds, but you get to any more distant keys and things start sounding awful. So in mean tone tuning, you have 8 pure thirds, you have 8 all right fifths, they're all flattened a bit, and then you have 4 thirds and 4 fifths that sound god-awful. So you're really restricted in the kind of music you write, just staying close to a certain key. But that's the kind of music they wrote at the time. They didn't stray too far from the key. So, let me make sure I'm not skipping over anything. Okay, so then there's the concept of the comma. And these are names for the various discrepancies that you have between different tuning systems. So, one of the most famous is the Pythagorean comma. So if you tune all your fifths pure and you end up back at C, how far is that from the 2-to-1 octave that we really want? Well, it turns out it's about a quarter of a half step off. It's too sharp by what we call cents, 24 cents. That's 1/100th of a equal tempered half step. And that's pretty far off. It's like the ear will not tolerate that amount of detune. There's other commas too. Probably the most important comma is the difference between a pure third, C to E, and the note that you get if you use Pythagorean tuning together. Go around the circle of fifths and end up on E. That's also almost a quarter of a half step off. It's 21.4 cents off. And these commas become the whole problem with how are we going to tune our keyboard instruments. Because no matter what system you use, there's some kind of a comma. Something doesn't match up. So, what are your solutions to this? Well, keep your music on one key, use just tuning, have all your intervals be pure, that's a solution. Or you can start to do what they call tempering. And that's where you do the things like, let's make all the fifths a little flat, not too flat, keep it tolerable. And that's when they start coming out with all these tempering systems, including mean tone temperament. So none of these earlier systems allow you to play satisfactorily in all 12 keys. They kind of allow you to hang out relatively close to one key. Somewhere around the mid-late 1600s, there was an interaction between composers and music theorists. They were trying to come up with tuning systems that allowed you to play in all the keys. And they started coming up with systems that are called well temperaments. This is not equal temperament. It's just tuning systems where you could play in any key, and the keys might sound different. Like F sharp might sound really different from C, but it would still sound tolerable and musical, right? And the first major well temperament was a system called Bergmeister III by a composer theorist named Bergmeister, and an organist and composer named Buxtehude, who was J.S. Bach's big hero, adopted this temperament. And in his compositions, he was starting to modulate to much more distant keys that required these kinds of temperaments. Now here's the conflict. The joy of musical sound had been these pure intervals, right? And with these new well temperaments, most of them, they might have a couple pure intervals, like, okay, we'll have this fifth be pure, the thirds are all going to be completely off, There are basically these strange compromises that end up bargaining away some of the foundational sounds of music up to that point. The perfect sonority between intervals. Now, on a guitar, you can actually hear these pure intervals by playing through the harmonic series. Because the thing about all these pure intervals is they occur naturally on any vibrating string. So for instance, if you play the low E, that's just our fundamental. And now if you lightly touch the 12th fret, you'll get the first harmonic. Wait, that's the fifth. That's the, to go to the 12th fret, right? Yeah, that's it, right. And then you get the next harmonic, the fifth. Yeah, exactly. And then next harmonic. Yeah. And then the next one's a little further up there. Yeah. So those harmonics give you these pure tones that we never hear anymore. And you could actually, some guitarists cleverly play them at the same time with other harmonics, or you could play it with another guitarist, and you would hear these pure intervals. And they are not present on the new equal tempered system. So what happens is in the 1700s, Bach and many people start pushing these well temperaments, which sound awful to the older style composers that like the pure intervals. There was people would rant against these new tuning systems. They're like, it's like forcing you to eat rotten meat and telling me that's going to taste good. Like you can tell me that it does. And so they were basically making this huge compromise with the fundamental sound of music, essentially just so they could change keys to more distant keys and play more complex, more chromatic music. It was interacting with the composition, it was interacting with the technology of the organs and how keyboard instruments were tuned. By the 1800s, you're starting to go past even these well-tempered systems and starting to go at least into the ideal of equal temperament. And this is where you have, a 12th root of 2. Now, accomplishing equal temperament by ear is not that easy. You have to have a really good ear to get these equal tempered half steps correct. And calculating the 12th root of 2 over 1 in terms of an interval, I'm sure there's piano tuners that can do this, but it really waits for the invention of these tuning systems, the little strobe piano tuners. I don't know if anyone remembers these things from when they were kids. They still used to use them that get you to the exact pitches that you want to get when you're tuning a piano.
Oh, that is so cool. Okay, there we go. Am I back on?
There we go. This has been so much more fascinating than I had any anticipation of, and way more math than I was expecting. I feel like we've hit the mark, and I think we need to do a part 2 coming up.
Okay.
So definitely write in and tell us what you think about Aaron and his awesome stuff, and then we'll have Aaron back on in a few episodes for part 2 of music theory.
Excellent.
Thank you so much for being here today.